Look up at the night sky. It's a vast, mysterious expanse that has fascinated humanity for millennia. Each twinkling point of light represents a star, a beacon of energy and light in the darkness. These stars are giant balls of gas burning bright across vast distances, illuminating the cosmos. Have you ever wondered what makes these celestial objects shine? What fuels their incredible light? The answer lies in a process called nuclear fusion, a phenomenon that occurs at the heart of every star. This is the very engine that powers the stars and our own sun, providing the energy that sustains life on Earth. Fusion is the process of combining light atomic nuclei to form heavier ones, such as hydrogen fusing into helium, releasing tremendous amounts of energy in the process, far greater than any chemical reaction. It's the fundamental force that has fueled the cosmos for billions of years, driving the evolution of galaxies, forging the elements that make up everything around us, from the carbon in our bodies to the iron in our blood. From the smallest atom to the largest star, fusion is the key to understanding the universe. Understanding fusion is not just about unraveling the mysteries of the universe, it's about unlocking a potentially limitless and clean source of energy for our planet. Imagine a world where we harness the power of fusion, providing sustainable energy for generations to come. Fusion is the ultimate source of energy for the universe, a testament to the power of nature. It is a process that occurs under extreme temperatures and pressures, conditions found deep within the cores of stars. In these stellar furnaces, atoms are stripped of their electrons, creating a plasma state. In this plasma, the magic of fusion happens, where nuclei collide and merge, releasing energy. This plasma is where the magic of fusion happens, a dance of particles that lights up the universe. This plasma is where the magic of fusion happens, a dance of particles that lights up the universe. Imagine hydrogen atoms, the simplest and most abundant element in the universe, moving at incredibly high speeds within the sun's core. These atoms are in a constant state of motion, driven by the immense gravitational forces and extreme temperatures found in the heart of our star. These atoms collide with such force that they overcome their natural repulsion and fuse together. This collision is not a simple event. It is a complex dance of particles, each interaction contributing to the energy that powers the sun. This fusion process, known as the proton-proton chain reaction, is the primary way our sun generates energy. It is a series of steps that transform hydrogen into helium, releasing vast amounts of energy in the form of light and heat. In the first step of the proton-proton chain, two protons, the positively charged particles found in atomic nuclei, collide and fuse to form deuterium, a heavier isotope of hydrogen. This initial fusion is a rare event, but it sets the stage for the subsequent reactions. This process also releases a positron, the antimatter counterpart of an electron, and a neutrino, a nearly massless particle that interacts very weakly with matter. These particles carry away some of the energy produced in the reaction. Next, the deuterium nucleus collides with another proton, fusing to form helium-3, a lighter isotope of helium. This step is crucial as it builds up the elements necessary for the final stages of the reaction. This reaction releases a gamma ray, a high-energy photon of light. Gamma rays are incredibly energetic and contribute to the sun's overall radiation output. Finally, two helium-3 nuclei collide, fusing to form a stable helium-4 nucleus and releasing two protons back into the mix. This final step completes the cycle, ensuring the continuous production of energy that sustains life on Earth. Deep within the sun's core, the temperature soars to over 15 million degrees Celsius, and the pressure is immense, equivalent to billions of times the Earth's atmospheric pressure at sea level. These conditions are so extreme that they create an environment unlike any other in our solar system. These extreme conditions are essential for overcoming the electrostatic repulsion between the positively charged protons, allowing them to get close enough for the strong nuclear force to take over and bind them together. This fusion process is the heart of the sun's energy production. Every second, the sun converts about 600 million tons of hydrogen into helium through nuclear fusion. This transformation is not just a simple change of elements, it is a profound release of energy. This process releases a staggering amount of energy, equivalent to the detonation of millions of atomic bombs every second. The energy produced in the core of the sun is so immense that it powers the entire solar system. This energy, in the form of gamma rays and other particles, slowly makes its way from the sun's core to its surface. taking hundreds of thousands of years to complete the journey. The journey of this energy is a slow and arduous process, but it is crucial for the sustenance of life on Earth. Once the energy reaches the sun's surface, it radiates out into space as sunlight, providing the light and heat that sustain life on Earth. This sunlight is the very essence of life, driving photosynthesis in plants and warming our planet. This constant outpouring of energy is a testament to the immense power of nuclear fusion, a process that has been ongoing for billions of years and will continue for billions more. The sun's energy is a reminder of the incredible forces at work in the universe. The sun, our closest star, is a magnificent example of the power of nuclear fusion, a process that not only fuels our solar system but also provides a glimpse into the workings of stars throughout the universe. Fusion is not just the energy source of stars, it's also the driving force behind their birth, evolution, and eventual demise. In the vast cold clouds of gas and dust scattered throughout galaxies, gravity slowly draws matter together. As these clouds collapse, they heat up, and the core becomes increasingly dense and hot. Eventually, the temperature and pressure in the core become high enough to ignite nuclear fusion, marking the birth of a star. For most of their lives, stars exist in a delicate balance, with the outward pressure from fusion counteracting the inward pull of gravity. However, this balancing act cannot last forever. As stars age, they gradually exhaust their hydrogen fuel. Massive stars, much larger than our sun, can fuse heavier elements in their cores, creating elements like carbon, oxygen, and even iron. These fusion reactions release increasingly less energy, eventually leading to the star's demise. Section 5. Earthbound fusion, a mountain to climb. Given its immense power and potential, scientists have long dreamed of harnessing nuclear fusion here on Earth. Imagine a future where power plants run on seawater, producing clean, safe, and virtually limitless energy. Fusion power holds the promise of a future free from fossil fuels and their associated environmental impacts. However, replicating the conditions found in the sun's core here on Earth is a monumental challenge. Creating and sustaining a plasma hot and dense enough for fusion to occur requires overcoming significant scientific and engineering hurdles. One of the primary challenges is confinement. Containing a plasma that's hotter than the sun's core is no easy feat. Scientists are exploring various methods, including magnetic confinement fusion, which uses powerful magnetic fields to trap the plasma, and inertial confinement fusion, which uses lasers or particle beams to compress and heat a small target. Despite the challenges, the potential benefits of fusion power are too great to ignore. Unlike fission, the process used in current nuclear power plants, fusion does not produce long-lived radioactive waste. The primary byproduct of fusion is helium, an inert gas. Fusion reactions are also inherently safe. Unlike fission reactions, which can lead to uncontrolled chain reactions, fusion reactions are self-regulating. Any disruption in the process would cause the plasma to cool and the reaction to stop. Furthermore, fusion fuels are abundant and widely available. Deuterium can be extracted from seawater, and tritium can be produced from lithium, a relatively common element. A small amount of fusion fuel can produce a tremendous amount of energy, making it a highly efficient energy source. Achieving practical fusion power would be a transformative technological breakthrough, akin to harnessing fire for the first time. It would revolutionize our energy production, reduce our reliance on fossil fuels, and pave the way for a more sustainable future. Imagine a world where cities are powered by clean fusion energy, where greenhouse gas emissions are a distant memory, and where the threat of climate change has been mitigated. Fusion power has the potential to transform our world for the better. While significant challenges remain, the pursuit of fusion energy is a testament to human ingenuity and our desire to solve some of the world's most pressing problems. With continued research and development, we can unlock the secrets of the stars and bring the power of fusion down to Earth. Despite the promise, fusion energy faces several hurdles. Creating the extreme conditions needed for fusion, temperatures hotter than the sun's core, requires immense energy. Confining this superheated plasma, a swirling soup of charged particles, is another significant challenge. Current fusion experiments consume more energy than they produce. However, researchers are making progress. Projects like ITER, the world's largest fusion experiment, aim to demonstrate the feasibility of net positive fusion power, producing more energy than consumed. Another challenge is the development of materials that can withstand the extreme conditions within a fusion reactor. The intense heat and radiation can damage reactor components, limiting their lifespan and increasing operational costs. New materials and designs are needed to overcome these limitations. Nuclear fusion is the process that powers the universe. It's the engine that drives the stars, forging the elements that make up everything around us. Unlocking the secrets of fusion on Earth holds immense promise for a clean, safe, and sustainable energy future. While challenges remain, the pursuit of fusion energy is a testament to human ingenuity and our determination to solve the world's most pressing problems. Just as we harness the power of fission, we stand on the cusp of replicating the very process that makes the stars shine, bringing a star down to Earth, not in the sky but in our laboratories and power plants. The journey to fusion power is a long and challenging one, but the rewards are immense. By unraveling the mysteries of the stars, we can unlock a future where humanity thrives on a healthy and vibrant planet, powered by the very force that created the cosmos.